So now that we've figured out what are cubic units and how to find basic, conversions between them, how about trying to find the volume of something? Well, if I can find the area of the base of a prism, all I have to do is multiply it by its height to find the volume. So in a rectangular prism, like you probably figured out for like a tissue box, you want to find the volume of that. Volume would be length times width times height. Well, what is the length and the width? The length and the width is really the area of the base. So you could think of volume of a prism as area of the base times height. And one reason that that's an advantage is, what if you didn't have a regularly shaped region? Like, you can memorize a formula for the volume of a rectangular prism, a triangular prism, a hexagonal prism, and so forth. But what if you had one of these things? I'm calling it a gift box. So it's not shaped like a rectangle. It's a combination of rectangles and such. How do you find that volume? Well, if you knew what the area of the base was, you could multiply it by the height to find the volume of that box. So you might want to take a minute and give this a try. Pause this video, see if you can figure out what the volume of this gift box is, and then we'll come back and we'll work on it together. All right, do you have an answer? There's two different ways that you can attack this, right? One of them is to take this region and divide it into smaller pieces. So I might take this piece apart over here, right? They tell me that these pieces are 5. So if this piece is 5, the 20 that's over here goes crossways, right, front to back. So if that's 5, then this piece here is 20. So this region here is 100. All right. Then this region across here, I know it looks like it's a different size, but it's actually not. That 20 that's in the front is the same as that 20 that's in the back, and the 5s that are separated are the same 5s here. So that's another region that's 100. Well, you might imagine I could do this more here and again here, and I'll have 4 regions that are each 100. Now, how about that big piece in the middle? Right, that big piece in the middle is 20 this way and 20 that way. So 20 times 20 is 400. So if I add up all those pieces, the 20 by 20 piece in the middle is 400, and then I add those 4 little pieces on the sides, 100, 100, 100, 100. I've come up with what? 400 plus another 400 gives me 800. That thing there is the area of my base. And then if you want the volume, multiply the area of the base times the height. So the area of the base is 800. The height is 10. The volume of my gift box, 8,000 cubic centimeters, right? Not square anymore. Square centimeters times centimeters is cubic centimeters. All right, there's another way that we could have done this too. Here, let me get rid of all the markings over here. Suppose instead of taking all the little pieces and adding them together, I took a bigger region and subtracted off the part that I don't want. So if I look at this piece here that's 20, and then that piece there is 5, and that piece there is 5. So the whole front of this object is really 30. And it goes back another 30. Except there's 4 pieces that I don't want. And those are the 4 corners here, right? By doing a 30 by 30, I've included these 4 corners that I don't really want as part of my object. So each of these corners are 5 by 5. So could I have said that the area of the base was 30 by 30, right? That's the whole piece, including the 4 extra pieces I don't want, and then subtract off the 4 corners, which are each 5 by 5. Right? 30 times 30 is 900. 5 times 5 is 25. 25 times 4 is 100, and then 900 minus 100 is 800. So I could have done it that way, and then obviously if I have that base that's the same, multiply it by the height, I still get 8,000 cubic centimeters. So you can do it that way too. Just like when we were finding areas of those funny looking regions, you can find volumes of those funny looking regions also by taking the whole thing, subtract off the parts you don't want, and you'll have the parts that you do want. All right, how about volume of a cylinder? All right. Remember, cylinders have circles as their bases? All right, so I got a cylinder. I've got circles for the base. I want to find the volume. Well, what is a cylinder based on? It's based on the radius of the base and the height of the object. If I want to find the volume of a cylinder, I can still use the same area of the base times height that I used for my prism, except maybe you want to adapt it a little bit to a cylinder, Well, the area of the base is pi r squared, so you can say the volume of a cylinder, pi r squared times the height. All right. Do you have to remember it as pi r squared h? No, you could think of it as area of the base times the height, and then just substitute in that area formula for the base. All right, so let's try a couple of these. I want to find the volume of each of these objects. Well, the cube is easy, right? Because if the cube has a height of 6, then every side is 6. So the volume of a cube is just the side cubed. I could think of it as area of the base times the height, except the area of the base is side times side, and the height is also the same length, so side times side times side, side cubed. So if I multiply 6 times 6 times 6, I think I get 216. Let's double check here. Yep, 216. And what are my units? Cubic centimeters. So 216 centimeters cubed. Right, if I want the volume of this right rectangular prism, so the measures are given in centimeters, I want to know how many of these little cubic centimeters, a cube that's a centimeter on every side, will fit inside this prism. So the area of the base is 10 times 3, which is 30. The height is 15, so the volume is going to be area of the base times height, 450. And what are my units? Well, I multiplied centimeters times centimeters to get the area of the base, so that's in centimeters squared. That's in centimeters. If I multiply centimeters squared times centimeters, I get centimeters cubed. All right, so the volume of my prism, 450 in cubic centimeters. All right, how about this right circular cylinder? All right, for this cylinder, the area of the base times the height, again, will work for a formula. Right? For all of these, the formula area of the base times height will work. In the case of the cylinder, the area of the base is the area of a circle. This one has a radius of 5, so I'll do pi times 5 squared. Area of the base is 25 pi. All right, so if you want the volume, multiply the area of the base times the height, and I get 250 pi, and I am in cubic centimeters. All right, base is going to be in square centimeters. Multiply that by centimeters again. I get cubic centimeters. All right, let's take a look at a can here. Oh, these are the answers. Good. All right, volume of the can of this of juice, right? It's a small juice can. 9.5 centimeters on one side is not a very big, not a big juice can. 5.5 centimeters across the top. Now, one of the things that I wanted to include here is that 5.5 centimeters is the diameter. The formulas that we're using are based on the radius. So if I want the radius of this thing, it's half the diameter. So take half of 5.5, and you end up with 2 3/4. All right. So for volume, you want the area of the base times the height. Well, the base is a circle, pi times the radius squared, and then multiply it by the height, which is 9.5. It's always good to throw in a couple of these problems that have a diameter given. You want the radius, makes you think a little bit about the formulas that you're using. All right, since these are given as decimals, let's throw them in. 2.75 squared. Then we're going to multiply that by 9.5. That gives me pi times, and then I'm approximating, so I'm going to end up multiplying this by pi anyway, right? 71.844. Okay, so now take that and multiply it by pi, because what I wrote there is already an approximation, so I've lost some accuracy to begin with. All right, so my volume is 225.70. What? Cubic centimeters. Good. Right, that's the volume of my orange juice can. All right, Cavallari's principle is sort of an interesting application of this, which is, suppose you had a stack of pennies, right? That's the best way I think to explain it. And the example here involves stacks of paper, but either one. If you stack 10 pennies from bottom to top, you could figure out what the volume of that stack was by calculating the volume of 1 penny and multiplying it by 10. Well, suppose you took those pennies and you stacked them so that instead of on top of each other, there was a penny, and then the next one was just a little bit off from there, and then the next one was a little bit off from there, and you stacked them so they still stood up, but they weren't quite on top of each other. Does the volume of those 10 pennies change? No, it's exactly the same volume because it's still made up of the same 10 pennies. It's just that they moved over. So instead of having 10 pennies stacked top to bottom, you've got the same 10 pennies except they're moved over a little bit. All right, same idea for a stack of paper, right? You've got, let's say, a stack of 100 pieces of copy paper that has a certain volume. Shift those pages over, and it's still the same volume. So it says two solids each with a base in the same plane have equal volumes if every plane parallel to the bases intersects the solids in cross sections of equal areas. So in other words, we're not changing the dimensions of those pennies that we're stacking. We're not changing the dimensions of those pieces of paper that we're stacking. Every cross section, every piece of paper in that stack has the same dimensions. It's just that we're stacking them a little bit differently. Doesn't matter, it's still the same volume. All right, you want to see pictures that deal with other objects besides stacks of papers? Here you go. Prisms, cylinders, and an oblique prism. So you can still find the volumes of those things using the same formulas. Area of the base times height will get you there. All right, how about volumes of other types of objects? Pyramids and cones. There are some neat applications out there, physical models that you can build to show people this, but if you can see through the drawings over here, if you were to take a prism, in this case a cube, right, a simple prism, area of the base times height, you can actually take that cube and separate it into 3 square pyramids. Those pyramids would have bases that are the sides of your cube. So take it apart, and you notice the blue one has that left side as the base, right? That blue one has this side here, so it's a square on the base. The green one has that side as the base, so that's a square. And the orangish one has that one as the base. So you can actually take that cube and separate it into 3 square pyramids. What does that mean? Well, that must mean then that the volume of the pyramid is 1/3 the volume of the cube. So if the volume of the cube was area of the base times height, then the volume of the pyramid must be 1/3 of that because there's 3 of them that will fit in a cube. And sure enough, there's the formula for the volume of a pyramid. 1/3 area of the base times the height. That same idea will work for a cylinder and a cone, right? You can take a cone, separate it from a cylinder in the same way, and you'll end up with the same idea. Okay. So volume of a pyramid, 1/3 area of the base times height. I made a note that the area of the base depends on the shape of the base, right? Is it a square? Is it a pentagon? Is it an octagon? What is it that's the base? You're going to have to calculate that separately, then throw it back together. That h represents the height of the object. So now compare the two of these things. What if the base is not a polygon? Well, it turns out that it doesn't matter. The formula remains exactly the same. In this case, this is an area of the base for a polygon. This thing is not a polygon. Okay, in fact, it's not even a circle. It's just an irregular region, as we call it. But it's still the same thing, right? If the base were a circle, we could replace that area of the base with a pi r squared. That's certainly possible, right? That's the area of the base. Same idea, though. So again, rather than memorize a bunch of different formulas, 1/3 area of the base times height will give you the volume for both a pyramid and the cone. All right, let's try one. Actually, let's try 2. So let's start with our regular right square pyramid. What do we need for the volume of these objects that have one base? 1/3 area of the base times height. So for this pyramid, the area of the base is 4 times 4, which is 16. The height is simply the height of the pyramid. So in this case, the height of the pyramid, it goes from the vertex perpendicular to the middle of the base, right? And it's a right angle, so it's perpendicular. So we're good. 1/3 area of the base, which is 16. Height is 5. And then we end up with what? An 80/3? It's not a whole number. That's okay. Cubic centimeters, right? Base is in square centimeters. Multiplied by another centimeter, you get a cubic centimeter. So the volume for my pyramid, 80/3 cubic centimeters. All right, how about my cone? All right, how do I find the base of my cone? The base of the cone is a circle. So we use pi r squared as the area of our circle. So pi times 6 squared will give me 36 pi. Right, the height was not given to me. Right? Here's the height. What do I know, though? I know that the slant height is 10, and I know that this base over here is 6, and what I've done is I've made myself a right triangle. Okay, so we can use the Pythagorean theorem to find that missing height. So if I do a squared plus b squared equals c squared, I can find the area of, if I could find the height of that object. So I get h squared plus 36 equals 100. Subtract the 36 from both sides. 100 minus 36 is 64. Okay. Take the square root of both sides. I'm only interested in the positive square root because I'm not going to have a negative height. Turns out the height is 8. If you remember 3, 4, 5 triangles, you can fill that in right away because 3, 4, 5 are the sides of a right triangle. Multiply them by 2, you'll get 6, 8, 10. All right, we haven't finished our problem yet, though. We have the area of the base now. We have the height. Volume is going to be 1/3 area of the base times the height. So 1/3 of 36 is 12. So I end up with 12 times pi times 8. 96 pi. What are we measuring this in? We're measuring it in cubic centimeters. Okay, so square centimeters was for the area of the base, cubic centimeters for the volume. I'm going to start another video and finish up the last couple of volumes, and then we'll work on similar figures while we're at it too.